So I will leave the word now for Keith. You're very welcome.
Thank you. Thank you for inviting me here. It's good to be back again. I was speaking in this room probably 5 or 6 years ago at a meeting on long-term experiments. And of course, you have some very nice long-term experiments here in Sweden, which I hope you're looking after very carefully, because the older they are, the more valuable they get. We can't quite match 200 years at Rothamstead, but we this year are 170 years old. So I think longevity has a lot to say for it, especially in the context, well, of perennials. We're perennials, and it's good to be in another perennial place. My co-authors, David Polson and Andy Whitmore, we've updated the talk a little since we wrote the paper in the European Journal of Soil Science. Every time we present it, we do share the presentations. We pass it round between each other and say, okay, what's changed, what's happened that's new, what new papers have come out. So it's reasonably up to date. And what's in here that is not in the European Journal paper is some information on grassland. I think grasslands are very difficult to monitor and to get some idea of carbon sequestration, but I've tried to bring something in to this talk. What we want to start with is this definition of sequestration. So we're thinking of soil as a sink, and okay, in terms of the dictionary definition, then any input of soil organic carbon into the soil could be called sequestration. But the focus tends to be climate change and mitigating climate change. And if we want to mitigate climate change, then we need some idea of permanency. In other words, not just a movement between compartments, but of some climate change mitigation and permanency, that the carbon will stay there. So it has to be a net transfer, and that's quite important for some of the processes that we'll look at. The main definition that I want us to get hold of is that transfer of carbon into the soil is finite. Okay, you might change the land management, you might come up with a system like perennial crops or zero-till that will increase the carbon in the soil, but it won't go on increasing forever. And that's quite important when we think about some of the claims that are being made for certain things that can be done, some management changes. This little graph shows it quite nicely, that you might start off with an initial equilibrium which is quite low, an old arable soil, and some of our arable soils are hundreds of years old. Indeed, the Romans were growing crops in Britain 2,000 years ago. So some of our land has been growing crops for probably thousands of years. And you might change the management system and you've got an increase in soil carbon, but that will reach a new equilibrium. It won't go on forever. And of course, the long-term experiments are perfect examples for showing that. And indeed, if you change the management system again, you could find yourself moving back down that curve and losing a lot of that carbon. And so when we look at the land management changes, we need to bear that in mind, that it's finite and it's reversible. The other thing to say is that in the context of climate change, many of the papers only look at carbon, but if you're really serious about climate change mitigation, you do have to think of the other greenhouse gases as well, like nitrous oxide and methane, because a little bit of nitrous oxide goes a long way, about 300 times more effective than carbon dioxide in climate warming. So if we don't take those gases into account, then we're going to cause a lot of confusion and maybe undergo some changes which aren't as beneficial. And then when we look at papers and look at the results, we need to think about whether they're as carbon or as carbon dioxide equivalents. And Jerry was presenting us, and indeed the first speaker, with some CO2 equivalent data. And it's sometimes quite difficult to see in the literature exactly what they're talking about, whether it's carbon or whether it's CO2 equivalents. I'll try and define which I mean, but it's not always clear to me. But the other thing to say, of course, is that extra carbon is really good for soil quality. So it's not just climate change that we need to think about and sequestration, but the quality of the soil and its ability, as Jerry was saying, to go on growing crops year after year. And a little bit of carbon going back in can make a huge difference, as we'll see. So the land use changes that I'm going to go through, just very briefly, that might give us some climate change mitigation and carbon sequestration are these. As I say, I've added grassland. Thought a little bit about duper rooting plants, but we've got another talk about that later, so I shan't say too much about that. And I'm going to mention dear old biochar. I don't know whether we have any biochar believers in the audience or watching us from overseas. In Britain, we have those who say that biochar is the answer to everything, and we've got others who say, no, it's a complete waste of time, it's not worth looking at. But we will spend a few minutes looking at biochar. So let's start with biosolids, animal manures, human waste, whatever. And we've done some calculations to look at how much of the carbon in biosolids goes back in, is retained in the soil. And it's about 25% on average year after year. That's from manure. The problem is, if you think about that as climate change mitigation, certainly in Britain, and I think in most countries, most of the manure is applied to land anyway. So you're not doing anything that's new. The manure is going to the land, the carbon is going in, so it's no good a farmer saying, oh, I'm mitigating climate change because I've just started to count the manure that I'm applying to the land, because they've always been applying it. Now, there is some genuine sequestration. If you're using organic waste that have been sent to landfill, completely not using it, it really is a waste product, not trying to get any use of it at all. And if you're applying that to land, then you're benefiting the soil carbon and maybe sequestering some carbon too. And this is the data from our old Broad Book experiment, 170 years old now. And here we're looking at the plot that gets 35 tons of farmyard manure per hectare per year. So a huge amount going in, but you can see that applying that builds up the carbon really quite quickly to begin with, and then, as I said just now, we're reaching that equilibrium value, but we haven't reached it yet after 170 years, so if you put on a lot, you can go on building soil carbon for a long time. This period here is when we had some problems with weeds, and we went into fallowing, and fallowing is a good way of losing carbon. But now we don't need to fallow again because we've got good weed control with herbicides, and so again we're back on this build-up curve there. So applying manures to land, yes, it's good for building up carbon, but if they went on to land anyway, not real carbon sequestration. And all of that is in this very nice paper by Johnny Johnston, that somebody you might know, in his 80s now, but still working on the long-term experiments, especially interested in soil organic matter. Other biosolids, one of the problems with applying organic manures or any biosolids is that you've got this risk of direct and indirect emissions of nitrous oxide, the indirect being from nitrate that's leached or ammonia that's emitted and redeposited and then converted into nitrous oxide. And so there is some emission of nitrous oxide whenever we apply organic materials to land. The evidence that I can find from this paper here is that the losses are very small. As a percentage of the N applied, it's not very much, it's less than 1%. But of course that's as nitrogen as nitrous oxide, and it is a very effective greenhouse gas. So when we're looking at budgets using organic manures and biosolids, if we don't take even that very small loss into account, we could completely misunderstand the climate change mitigation of applying that loss to land, that manure to land. We made a review for our Department for Environment, Food and Rural Affairs, where we looked at the impacts, the increases in soil organic carbon of these various materials applied to land. These were the application rates, and this was the potential increase in soil organic carbon in kilograms per hectare per year, tons of dry solid. And so there is an increase in soil organic carbon from applying these. Digested biosolids is the biggest because they've been digested, and so a lot of that carbon has already gone back to the atmosphere in the digestion process. And that's another thing we have to remember, that if we compost manures, if we compost waste material, we lose a huge amount of carbon in the composting process. But there is some build up in soil organic carbon by applying these materials. And if you think that much urban waste from gardens, from trees, from parks, that was just discarded years ago, composting it and using it back to land must be good in terms of carbon and in terms of sequestering carbon. So there's some real benefits there. Crop residues, we reckon that about 22%, so almost the same as the manure, about 22% of the residue that's applied is retained by the soil, and most of that residue is mineralised and returned to the atmosphere within the first year. It breaks down very quickly. If it would have been applied to land, which a lot of it is, then even if you apply it to another farm, there's no real sequestration benefit. The only benefit would be, as we used to, if we burn the straw. And in Britain, that was banned well over 15 years ago now. But we used to burn it because it was a good way of controlling pests and weeds. Farmers thought a good burn across the whole field would destroy weeds, and indeed it was very effective. So in that sense, of course, we've stopped a process that controlled weeds. Farmers now use more chemicals to control the weeds, but they're not causing the smoke and the nuisance that straw burning caused. But it's not sequestration unless that straw would have been used for something else, those crop residues. It's very interesting to look at the effect on total carbon, and we've got some results here from an experiment in Denmark where we did some collaboration. The impact on total carbon, total nitrogen is really very small. But the interesting thing is this big increase in microbial biomass, the living and active part of the soil. You get this big increase just by returning crop residues. In this case, it's straw incorporation. And that increase is really very valuable for encouraging the active dynamic food web processes in the soil, feeding the organisms, in other words. So although it might not have a big impact on total carbon and nitrogen, it's really important for soil quality and for feeding the living organisms and getting that nitrogen cycling going that Jerry was talking about. But there are alternative uses. One can burn straw. We're burning straw in the UK for electricity generation. Indeed, we're burning wheat in the UK for electricity generation because the power stations are obliged to burn so much renewables, and often wheat is the best source of that. So we've got the crazy situation that we burn food to produce energy. It's a little bit like in the US, you're using crops for biofuels instead of for food. It secures the fuel supply, and in the UK it helps energy production, but it's a pretty crazy way of looking for sustainability. Anaerobic digestion, that can produce biogas, good for local energy production, and of course if you put the residue back on the soil then you get some benefit. And actually we think that if you do a life cycle analysis then you get better climate change mitigation by burning and by digestion than just putting the material back to the soil. But of course life cycle assessments are prone to lots of approximations and we don't always bring every aspect in. So I think that has to be considered very carefully. But nevertheless, David Paulson did think that if you burn the straw or if you use anaerobic digestion and then put the residue back on the soil, that's the best use of crop residues. We might like to discuss that later. Fertilizers, well, especially nitrogen, you get an increase in crop yields from applying a reasonable amount of fertilizer. You need to match the amount with a good estimate of the crop yield that you can get, which will depend on the soil and the weather. And of course, because the crop yields are increased, then the returns in roots and residues are greater. And that's a genuine transfer of carbon from the atmosphere to land, and it's an increase in food production. So a moderate application of fertilizer could be seen as a good thing. And indeed, if you look at soil organic carbon on broadbulk, so you're looking at an unmanured plot yielding round about a tonne per hectare per year of wheat versus a fertilised plot yielding up to 10 or 11 tonnes per hectare per year, there's a very small increase, 0.4 tonnes of CO2 equivalent per hectare per year, but only for about 50 years, and then it reaches this new equilibrium. The problem is you've got greenhouse gas emissions, CO2 and N2O, from both manufacturing the fertilizer and then losses of N2O and nitrate and ammonium after application. And if you do a more effective balance, then just applying 144 kilograms of N, you're emitting about 0.6 tons of CO2 per equivalent per year, so more than the carbon that you're fixing from that fertilizer, which means that fertilizers don't look to be a good way of sequestering carbon and mitigating climate change, certainly not in terms of that balance. And of course, we're still applying them today, long after the soil organic carbon content has stabilized. So we're still applying nitrogen, we're still losing or emitting greenhouse gases from its manufacture and from the nitrogen losses. So you can't really say that applying fertilizer is a way to mitigate climate change, certainly not if you look at a calculation like that. Min-till, zero-till, lots of claims for carbon sequestration for that. Ratan Lal from the States was a very big proponent of min-till and zero-till. We don't think the benefits are quite so great, and talking to him recently, he's modified his views a little bit. These are the problems, that yes, you can get some sequestration, but we think a lot of it is about redistribution. So with min-till and zero-till, a lot more carbon at the surface, but less below. And I'll show you an example in a minute. There's probably some small net carbon accumulation. The problem in the UK in particular is that we go in for rotational min-till and zero-till. We have particular problems with perennial weeds, and so our farmers they like the idea of zero-till and min-till, but when the weeds begin to develop, then they plough it up in a conventional tillage way, and so you lose all the benefits of zero and min-till as soon as you plough. There are also, we think, increased nitrous oxide emissions from zero and min-till. In the first few years, you tend to get more compaction in the soil, and so it's wetter. And that's perfect conditions for the process called denitrification, which produces nitrous oxide. And so we think in the first few years of min-till, the nitrous oxide emissions probably outweigh any carbon sequestration benefit. But we do think that if you can go in for long-term min-till, zero-till, the earthworms get going, the soil structure improves, that initial compaction and wetness is overcome, and probably then you will begin to see net carbon sequestration and climate change mitigation. But unfortunately, we don't have any long-term min-till experiments in the UK, and I'm not sure of many where greenhouse gases and carbon have been really effectively monitored. So we can't really be sure of that. But that's our supposition, our interpretation of the data that we've got to date. And this is just some information from Pedro Machado from Brazil, where we looked at reasonably long-term, 26 years reduced tillage on a soil in Brazil, whole soil carbon. Then you've got this redistribution with more carbon in the surface, but less at depth, so no net benefit. But again, if you look at the free light fraction, very available carbon that's going in, then there's a real benefit of that in the surface soil, and really quite a significant increase. And that's good for soil organisms, for soil structure, water holding. So some benefits of min-till in that limited context. So overall benefits, probably or possibly a small soil organic carbon accumulation. You may be aware of the Stern report, which was written in the UK, looking at the economics of mitigating climate change, when Stern was very positive about the need to move towards technologies and businesses which were seriously looking to mitigate climate change and change to green technology. So he's saying about 0.4 tons, 140 kilograms of carbon, just carbon per hectare per year. We reckon it's something like between 300 plus or minus 180 tons of carbon per hectare per year. But of course that doesn't include the other greenhouse gases, that's just carbon. And as I said, we plough the land every few years anyway, but there are benefits in the surface soil for structure, for seedling emergence, water retention, whatever. So some benefits from zero and min-till, but not always in terms of carbon sequestration and climate change. And the problem is, as I said, if you just look at nitrous oxide emissions, an extra 3 kilograms of N2O will offset that 300 kilograms of carbon per hectare per year that we estimated was sequestered. And we reckon we found 4 kilograms N2O emitted in some of our short-term no-till, min-till experiments. So it looks as though the nitrous oxide in the short term is completely outweighing any benefits of carbon sequestration. No consistent pattern, but probably an increase in N2O. And the other thing to say, of course, is that if you look at overall global warming potential, all the greenhouse gases, then most agricultural systems produce a net increase in global warming potential. It's very difficult to grow food and not cause climate change. So perennial crops might be one way that you could do it. But our understanding, our interpretation of the information at the moment is that it's very difficult to manage the land, to grow crops, to feed 7 billion people, 9 billion people without causing some climate change. So we have some serious issues to wrestle with there. Now, if you could convert arable land to grassland or forest, then that really is genuine carbon sequestration. And there's a very rapid build-up of carbon. I've got some data in a minute. But of course, if we in the developed world say, well, we're going to mitigate climate change because we'll move some of our arable land to grassland and forest, if we do that, but then buy our food from overseas, and Brazil or a tropical country, they deforest the land, plough it up, or drain wetland, then essentially all we're doing is exporting our climate change. So we're not really benefiting the globe at all. So it might be something that could be done, but I suspect with limited land and limited soil, as Jerry showed us, then converting arable land to grassland and forest is not going to happen, not on a major scale, and it wouldn't be good for the globe anyway. So we have to look for other methods. There is some increase in methane oxidation, not just carbon sequestration, but because of the way the soil structure is improved, then methane oxidation is increased, so you get less emission of methane, or actually a removal of methane from the atmosphere. And you also get a reduction in nitrous oxide emissions, provided the air is clean and there's not too much nitrogen deposition. We're in a very polluted part of Britain, and this little bit of woodland here at Rothamstead might be getting well over 100 kilograms of nitrogen per hectare per year, because the woodland is so good at scavenging nitrogen out of the atmosphere, and we've got nitric acid, nitrogen oxides, ammonia, all being deposited in our area because it's urban, semi-urban, so a lot of pollution. And we've got very large emissions of nitrous oxide. In fact, they're bigger than the emissions on the Broadbulk experiment on the plot that gets 300 kilograms of nitrogen fertilizer per hectare per year. It's only a little bit of woodland, so it's not really representative of the whole of the country, but if you've got a little bit of woodland like that in a polluted area, the nitrous oxide emissions can be enormous. And so it's worth bearing that in mind when we think about the benefits of woodland. Arable to grassland, this is the kind of benefit you can get. This is old arable land, probably been growing crops for hundreds of years, converted to grassland. Very rapid build-up of carbon, but again reaching this equilibrium value. Not quite yet. It's about 60 years old now, so a little way to go before it gets to equilibrium, but a really big benefit in soil carbon there. Then we've got old grassland that's been grassland or was grassland for many years, left in grassland in about 1949. Left in grassland a small increase to this equilibrium value that one will eventually get to. But if you plough it up, a very rapid loss of carbon. So any pressure to plough up old grassland, or indeed to remove forest land to produce more food, is going to cause us real problems in terms of carbon loss and climate change. I suspect most of us know that already, but it's nice to see some data from really long-term experiments which show you how big that can be and how long it will go on for. And that's been one of the issues that those who use palm oil have had to wrestle with, where large areas of tropical forest have been removed to plant palm oil. Okay, the palm oil is a renewable energy resource. It's needed in various products. But the carbon loss from the forest and the soil where they've removed the tropical forest is huge. And the estimates are that it would take 100 years of the palm oil plantations before there was recovery of the carbon lost from removing that tropical forest. So that's not been good for climate change at all. It might be necessary for producing soaps and whatever, but it's been really bad for climate change. Arable to forest, arable to woodland. We've got some old arable land on our long-term experiments which was just fenced off and left in 1882, 130 years old now, and of course it's been accumulating carbon. The woodland has been growing and developing very rapid increases and very large increases in carbon if we could convert arable land back to woodland or forest. But for us in the UK, okay, we are rewooding some of the land, and that's potentially good, but I don't think we've got very much arable land that we can afford to do that with because of the demand for food supply. And this little diagram here just shows you where that carbon is going, quite a lot of it into the above ground trees, fair bit of it into the roots, and a nice increase in soil carbon. So just shows you the distribution. So grassland systems. This is not what we had. Am I making a funny noise, by the way? It sounds a bit weird to me, but it's okay to you? Okay, fine. Perhaps it's a bit of feedback. I'm not used to the Madonna-type headsets, but I won't sing, I promise. I managed to find some information from the literature that's come out fairly recently. This work by Jean-François Susanna and his colleagues in France. They've looked at 9 European sites and tried to get some estimate of net carbon storage. Just carbon, as I understand it. And there's a big difference between grazed or cut systems. But then they've also tried to include nitrous oxide and methane. And when they do that to get the overall CO2 equivalent budget, then it looks as though across the whole systems, then they think they're sequestering about 400 kilograms of CO2 per hectare per year, which looks pretty good. But as I said right at the beginning, I don't think one can go on sequestering carbon forever, so I'm not sure where that system started from, whether it's relatively new grassland or short-term grassland. I suspect it's not very old grassland, but I don't have that information. So I think that's quite critical. And we also found some other information. The National Soil Inventory in England and Wales, they looked at rotational grasslands and thought they were accumulating about 100 kilograms of carbon per hectare per year. That looks pretty good. In Belgium, huge variation, plus 400 to minus 900 kilograms of carbon per hectare per year on their grasslands. So enormous variation. Another European carbon balance by Janssens, 600 plus or minus 900. So enormous variation. And then this work by Follett and Schumann, grazing land, 19 regions around the world. And they thought over this 3.5 billion hectares of permanent pasture, they thought they were accumulating about 60 kilograms of carbon per hectare per year. So a small amount, but if that's correct, then that shows that grasslands are beneficial. And putting it all together and trying to make it into CO2 equivalents, then these are the numbers that I came up with in terms of CO2 equivalents. So trying to think of the other greenhouse gases as well. And it's round about 200, 300, 400 kilograms with huge variation, as these data show. But it does suggest that grassland is a good way of accumulating carbon, but I'm not sure where these are in terms of the equilibrium, and so I would be very wary about wanting to claim that grassland is always good for accumulating carbon. It's got to come to equilibrium at some stage, and maybe even a slight change in management, climate change and global warming, that could begin to cause a loss of that soil carbon. So some hope there, but some issues as well. We've got a whole paper on deeper rooting crops later, but our chief executive, Douglas Kell, wrote this paper in Annals of Botany just a year or so ago. He's very enthusiastic about this. That's partly because the IBERS, the research centre in Britain that breeds grasses and clovers for grazed pasture systems, they are beginning to produce grasses with deeper roots. We realise that we've been breeding crops, including grass, for the above ground production, but we really need to look at what's happening below ground. And so our crop breeders are beginning to think about rooting, root distribution, root depth, and so we're coming at it. Jerry was talking about perennial crops. We're coming at it from the point of view of annual crops having better roots. So two different directions, but the same kind of aim. And if you've got deeper rooting crops with bigger roots, better roots, then there's some option there for sequestering carbon at depth, in other words, below the plough depth. So it might be protected more effectively. Maybe there are options for biocontrol of pests and diseases, inhibition of nitrification, and we're looking at that a little bit, whether some of these crops would exude various chemicals that would restrict some of these processes. So some options there. And we think we've got some data from a 14-year-old miscanthus trial where we've got certain varieties where below the plough layer there's some indication of some carbon sequestration at depth. Small amounts, but it looks to be real, and we've tried to measure that with delta 13C. It's not every variety of miscanthus, but there are some options for these deep-rooting crops sequestering carbon below plough layer. So some optimism there. A few words on biochar. We know what it is. It's not just charcoal, it's material that's pyrolyzed under very carefully controlled conditions to produce a particular product with a degree of porosity and cation exchange capacity, active surfaces. It's very stable, or at least it's claimed to be very stable, but people are beginning to question that. Lots of proposed benefits for soil, increases in soil carbon stabilization, better crop performance, water holding capacity. The problem is that there are huge gaps in understanding it. There are, as far as I'm aware, no really good field experiments where it's been tested under realistic conditions and where one might be able to prove to farmers that it's as beneficial as it's claimed to be. Lots of lab experiments. We've got a small field experiment at Rothamstead, but not enough data yet to prove its benefit. And so you've got people trying to sell it and promote it, and you've got others saying, no, it's, as I said at the beginning, complete waste of time. But we do need to test it and see what the benefits are. So that's my summary of carbon sequestration. So we've got kilograms per hectare per year of CO2 carbon, so that's CO2 equivalents from these various different things like min-till, no-till, application of biosolids, and I've tried to add grassland at the end. In some cases, then adding these materials are actually beneficial in terms of nitrous oxide and methane. So you've got some reduction in nitrous oxide emissions under some cases, but in others you appear to have some increase in nitrous oxide emissions and so some reduction in the CO2 benefits. And for grassland, very uncertain. Again, none of these have error bars on because they're all estimations, approximations, very difficult to put error bars on it. But if you do have something like paper crumble, that's waste from the newspaper industry, if you apply that, then you can get a very large amounts of carbon locked up in the soil. But then, of course, as you do that, you also lock up some nitrogen. So you'll need to apply some fertilizer nitrogen to compensate for all that carbon that's going in. Otherwise, you'll completely muck up the nitrogen cycling system and ruin any crop yields there. Maintaining soil organic carbon in cropping systems, well, layerable farming, if you have a system that allows that. In Britain, we have almost complete separation of arable and livestock, and in arable systems, the most productive is a wheat oilseed rape rotation year after year. It's best in terms of economics, but it's not really good for soil quality, and it's certainly not good for sequestering carbon. Adding residues, all these various things, we've talked about them, plants with longer roots and fertilizers. So there are things that can be done. Fertilizers on a really poorly producing system with low yields, then applying just a little bit of nitrogen fertilizer to boost the yield will give you a better crop and a better crop return. So there might be some benefits on really poorly producing systems. For grassland, then clearly avoiding tillage. That's absolutely essential. As soon as you cultivate it, huge losses of carbon. Moderately intensifying poor pastures, that can increase the growth and increase the root growth as well and sequester some carbon. Light grazing, not heavy grazing. Mob grazing, I've not talked about that. It's becoming quite popular in the US, in Australia. They've tried to sell it in the UK, hasn't taken off at all. So I think there's a lot to be discussed about this idea of mob grazing. Increasing the duration of grass lays in rotations and converting grass lays to grass legume mixtures. We're looking again at the quality of our grass. We've gone for pure ryegrass swards for many years now because of the yield, but people are worried about the quality of the forage as well as the productivity. So conclusions, not everything sequesters carbon. Some does. Incorporating organic waste can be beneficial. But it depends on what was done with the waste beforehand, but it certainly benefits soil quality and functioning, and maybe you get better climate change mitigation from burning or digesting biosolids. Large greenhouse gas emissions from end fertilizer manufacture. It's probably as efficient as it could be, but the emissions are still enormous, and so we need to think about that when we're looking at carbon sequestration from crop residue returns. Min-till, zero-till, probably good in the long term, but if you're in rotational min and zero-till, then no. And conversion of arable land to forest and grassland, yes. But how much can we do that with the demand for food for 9-10 billion? And generally, we think there's far too much emphasis just on carbon. We need to think of overall climate change effects if we're looking at climate change mitigation. The risk is of land clearance for food or biofuels, deforestation, wetland drainage still going on in many parts of the world. So we need good land stewardship and we need integrated solutions. Don't just think about carbon, think about nitrogen, phosphorus supply, water. All these things need to be brought in to come up with sustainable agricultural systems. Thank you very much.
Thank you very much. I think I get the questions here directly.
Thank you very much. We all know about this unique series of measurements you have in Rothamstead on these grass plots for whatever it is, 140 years now. There was one treatment I missed, and maybe it's a treatment that is kind of interesting when you look at yield. You showed that there was no manure applied, there was NPK applied, and there was manure applied.
Yes.
But there was not a combination of NPK and manure.
No.
Which from a yield point of view, normally in 90% of the cases turn out to be the best treatment, at least in tropical soils.
Yes.
And I assume also in temperate soils. How could you speculate what would be the underground effect on biomass if you did combine the two? Can you?
Well, we do have a treatment on Broad Brook that gets manure and some extra fertilizer in spring, but we have not made extensive measurements on that soil in terms of looking at the changes in carbon or the changes in the biomass in the soil, but we could do it. We would recommend that returning the manure, recycling the manure, plus fertilizer where it's needed is the best way to manage the manure, to utilize it effectively, but with an understanding that it will never be able to supply the exact amount of nitrogen that the crop needs. So you need to combine the two. The problem is that applying manure, as we apply it in very large amounts and probably generally, because the nitrogen is mineralized throughout the year, and under our climate, especially in the autumn, the losses of nitrogen in the winter are very large under our system. So recycling manure, yes, it's good. It's good to reuse that nitrogen and phosphorus and potassium, but one has to be realistic about the amounts that are going to be lost year after year from recycling like that. But I don't know in the detail about what the benefits of below ground would be, but I'm sure applying manure would be beneficial, and a little bit of extra nitrogen just to get the best yields is probably good too.
Okay, you spoke of grasslands as if they would not produce very much food, and to me, our ruminants should be considered as a part of the soil.
Yeah.
And I would suspect that those nice figures you had from Belgium or somewhere were because those grasslands were producing a lot of food with the help of ruminants. They do better performance.
Yeah. Oh, I'm sorry if I gave the impression that they weren't important for food. They're incredibly important. And of course, in some parts of the world, grassland is the best crop to grow. In the west of Britain, it's not really suitable because of the climate and the topography for growing crops, but for growing grass and for grazing animals, dairy cattle, beef, sheep, it's absolutely perfect. So yes, they're incredibly important. And you're right, those variations were probably in the highest productivity areas. The challenge for us is to recycle the waste from those livestock in a system where it's probably better to put it back on arable crops, but the arable crops are hundreds of miles away in another part of the country. But I wouldn't want to give the impression that grassland is not productive, because it is.
My name is Peter Sylvan. I'm a member of the Academy. When you look at the curves of carbon increase from Rothamstead, I mean, we all agree, I suppose, that you reach an equilibrium, you have to do it. But I think it's interesting to see that it's rather takes quite many years. I mean, the figures I have in here from the Highland and Foster Layerable.
Yes.
I got it from you. It started in 1945 something. And when you reach, it's still increasing in 1990, and that is 50 years.
Yes.
So, and I mean, if you compare that with the quotation from Douglas Kell, you mentioned his name.
Yes.
When he has, I suppose you know, there's quite a famous citation from him in Scientific American, I think, when he said that if you can convert 2% every year of the global agricultural land into perennials, it will be sequestered enough carbon to count up for the whole industrial outlet of carbon dioxide.
Yes.
Industry and farm. Could you give us a comment on these very optimistic calculations?
Yes, Douglas is very enthusiastic about deeper rooting crops and perennials. We are not quite so optimistic as he is. But of course, those kinds of calculations are interesting. But do you think we can afford to convert even 2% of the arable land into, well, certainly grassland? I'm not sure. The Brazilians are busy converting the cerrado into arable production, so they're going the other way. Yes, maybe perennials are the way to go, but maybe also these new deeper rooting grasses that we're producing, because that's where he's coming from. He's very enthusiastic about the work going on at Aberystwyth on these new grasses. So I'm not quite as optimistic as he is, but I think there are possibilities.
No, but given the opportunities we have today, of course, it's absolutely incredible, unbelievable. You couldn't think about it.
No.
But I mean, if you put the perspective of perennials producing not 5 ton per hectare, but 10 ton per hectare, or in cereals, I mean,
yes.
What do we have science for if not being very long-sighted?
Yeah. Well, we have a program that is aiming to produce 20 tonnes of wheat per hectare in the next 20 years. So we're looking to modify photosynthesis, nitrogen uptake use efficiency, using genetic modification at the moment, and that target is to sort of, as I say, 20 tonnes of wheat. So we're looking into the future from that point of view, and we're testing these deeper rooting grasses on one of our grassland experiments down in the West Country. So yes, we're looking into the future, but I suppose I'm thinking about the now and what can be done in the next 5 to 10 years rather than in the 20 to 30 year.
But those 20 tonnes can come also from perennials?
Possibly. Jerry's smiling. We'll see.
We let Jerry have.
Yeah, thank you. Thanks so much. That was a wonderful overview. I wonder if your data is on a per hectare basis mostly,
yes,
without much mention of yields.
Yeah.
So have you considered on a per yield basis? And I ask that because I can imagine a situation where one system might result in a lot of greenhouse gas emissions, but also a tremendous amount of grain production, for example.
Yeah.
That would be preferable over a low greenhouse gas but
yes.
low yield system anyway.
Yeah. There's a very nice paper by Van Groningen, I think, and that group, where they've looked at nitrous oxide emissions, and there's essentially a minimum, or at least a degree that you should go if you calculate the emissions on the basis of productivity. And it's clear that if we want to produce more food and we want to mitigate climate change, we need to look at emissions per unit of product. And that gets you some very different answers, as you were saying. And there's clearly an optimum fertilizer application, an optimum system, which gives you the minimum in terms of global change. And we've also done it in the context of, well, we've called it overall sustainability, looking at biodiversity, looking at climate change, greenhouse gas emissions, water quality, using something called total factor productivity, which puts a monetary value on everything, which is controversial, but everybody understands money, so you have a basis for discussion. Because you can say, I want more birds. Okay, so how much do we need to value the birds? Or how much do we need to pay the farmers for the food? And doing that per unit of yield, you get a very clear indication of what's the best system in terms of sustainability. But it doesn't produce everything that we would want. There's going to be some climate change, some degree of water pollution, some loss of biodiversity, and everybody's going to have to debate about which is the best system for them. But per unit of product is really important. Yeah.
A question for you here.
Hey, my name is Lucy Carver, and I'm wondering about the studies that you've done, what kind of soil type they're on, and also have you done studies on different soil types and whether I'm wondering whether there are significant differences depending on the soil type.
Yeah, these soils at Rothamstead are all what we call flinty, silty clay loam. They're about 20-25% clay, reasonably easy to manage, but full of flint stones. We've also done studies on sandy soil, 10% clay, and of course the amount of carbon that the soil will hold to some extent depends on the clay content as well as the management system, because there's a degree to which carbon is protected by the structure of the soil and by association with the clay. And so the greater the clay content, certainly the greater the minimum amount of carbon that a soil will hold. But there's a huge range dependent on climate and management at each clay content over which the carbon content varies. So it does vary with soil type and climate and management as well as management. Yeah.
Thank you. Mike Jones again. Talking about livestock production in the west and southwest of England, recently there's a lot of arable farmers there because of the fluctuation and very unpredictable weather patterns, thinking thinking seriously of getting out of arable production altogether and shifting into grassland and grass-fed beef and that sort of thing. What kind of policy support might they expect, and what kinds of work are you doing that might help the government or move the government to provide the right kind of policy support?
For the last 20 years, most of the policies have seen agriculture as a problem. I think we heard it back at the beginning. Agriculture is causing most damage, it's polluting the environment, etc., etc. So all the policies have been about protecting water and minimising loss, whatever. We have a new farm system study down in the southwest where we're going to be comparing different grassland production systems for beef and sheep, not for dairy, but we're going to look at legumes to replace or at least partially replace fertilizers, the deeper rooting grasses I was talking about, novel management systems. And so working with farmers, we're going to be looking at grassland management which would help them to manage their systems better, to increase productivity while minimising environmental impact. And we hope that that will be an assistance to them. The government is beginning to think about food security. The Department for Environment, Food and Rural Affairs has a sustainable intensification research platform, but we don't know what that's going to fund yet. So they are beginning to think about research to support farmers in the southwest and in other parts of the country as well. But the system of translating that research has broken down in the UK and probably in other countries too. We no longer have a national extension service. And so people like me are supposed to do our research and produce papers for Nature and Science, because that's what my bosses want. But we're also supposed to go out and talk to farmers and tell them what to do. And that's quite a different skill. So one of the things we're having to do is work with socioeconomists and learn their language, which is completely different from natural science language, but it's quite exciting for those of us who like to do it. And so working with them, we can learn how farmers think, what influences them, what drives them. Is it what they've always done? Is it what the farmer next door does that looks pretty good? Is it a piece of paper that somebody sends them? It's certainly not a research paper that I write because they never read them. So big challenges in supporting farmers, whether they're getting out of arable or whether they're staying in dairy, whatever. But we're doing our best to help within the limitations of our skills and knowledge. But I think we need to rebuild extension and translation with people who know how to do it.
Okay, we are running out of time. Jürgen, you will have a very short question. No, not you, sorry. Well, okay.
My name is Ulf Johansson, and I'm thinking of people who buy cars and biofuels, and they don't get the right figures regarding emissions since everything is not included. And do you see any possibility to fix that problem? For instance, a global, since it's always a mixture between different sources of fuel. So should we make a calculation of global average values or something that we can use?
Well, I'm a soil scientist. You're really dragging me way outside my comfort limit. People talk about carbon credits, and one of the big problems we have is how those are fixed, what value is put on carbon. And until our governments really get a serious handle on that, I don't think we can go very far. But the other problem with vehicles that use biofuels or indeed renewable energy and hybrids, you've got the cost of non-renewable resources to make the engines, lots of precious metals. There's some really big issues about overall sustainability of any kind of vehicle, and it's not just about carbon and oil and biofuel, it's about the other things that go into them as well. So I think, again, it's this problem of integrated solutions and how to get politicians and policymakers to try and think of the bigger picture when they like single questions and single answers to those questions. And invariably, if you give them that, you cause a problem somewhere else.
Thank you. That would be the last. I'm very glad that there are so many questions here, and I think it's great and it's wonderful that we have got these very good speakers from England and United States. I'm glad for all the questions.
Thank you.
I will thank you.